Okay, listen up and watch carefully here, guys. So, question number one, we've got that we're looking for the final velocity of a boat that's accelerating from rest. Rest tells us what? That the initial velocity is 0, tells us the time, and tells us the rate of acceleration. So, give them a mark for their givens. Okay, VF is the thing we're looking for. We started from rest, 13.4 seconds, 4.5 meters per second squared for a rate of acceleration. Okay, if we want to solve for VF, the first thing we do is multiply both sides by t so that it cancels over here and comes over here to be t times a. Okay, then I've got to add vi to both sides. Vi was 0 anyway, so it really just kind of goes away, right? And we have t times a because it's 0, right? And 0 plus anything is anything. All right, so if they have that formula, a equals vf minus vi over t, give them a mark. Okay, give them a mark if they manipulated it correctly. Okay, give them a mark if they plug the numbers in correctly, whether they have the 0 there or not. I mean, it doesn't really matter mathematically. 13.4 times 4.5. Okay, and that should give us, and I have the wrong number of significant figures here, it should just be 60 meters per second. There's only 2 significant figures in that question. Okay. All right, so that one is out of 5. Any questions on number 1? Okay. For question number 2, tells us that the object reaches a speed of 29 meters per second, so they gave us VF this time, okay, after accelerating at 7 meters per second squared, so they gave us A, okay, and they gave us the time, 2.9 seconds. We're looking for its initial speed, or VI. So, mark for givens, VF 29, A 7 meters per second squared, T 2.9 seconds. Okay, another mark for picking the formula. And I know on a quiz entitled acceleration, that seems like a silly mark to give, but I'm giving it anyway. Okay, on a unit exam, it's a valid mark because you have to identify what kind of question it is. And if you identify it as an acceleration question correctly, you deserve a mark for that. So that's why that mark is there. Okay, now we're going to be manipulating for VI this time. So I'm again going to multiply both sides by t so that it cancels. I'm going to add VI to both sides so that it becomes positive, and I'm solving for a positive number, right? And then I'm going to bring t times a over to this side by subtracting it. All right, so again, we want to think logically about this. If I have my final velocity minus how much my velocity changes by, t times a, that should give me what I started with. Everybody all right with that? Okay, so give them a mark if they have the proper manipulation. Vi equals vf minus t times a. They may have also had t times a minus vf equals negative vi, and if they had that, that's still valid. Okay. And then a mark for plugging in the numbers correctly, 29 meters per second minus 7 times 2.9. And that should give us a final answer to the right number of significant figures this time, 8.7 meters per second. Oh, sorry, no, it's only 1, so it's got to be 9. I'm looking at 7 there. Yep. 9 meters per second. I was thinking in my mind that was 7.0. Okay. Mark out of 10, please. Let them see it, and then put them in a pile next to my coffee cup on this desk here. Yeah. Okay. So, the lab we're going to be working on today, guys, okay, is a lab that's going to allow us to figure out what the relationship between force, distance, and work is. We started looking at that yesterday, okay, and we looked at how the formula for work is force times distance. It's actually technically average force times distance, but I mean, we just write force times distance. Okay? In that way, it works very much like this formula does. D equals V av times t, which we use sometimes to do with velocity versus time graphs, right? If we wanted to calculate the displacement of an object, we use the average velocity times time. Sometimes that was the area underneath the line or things like that. Okay, well, we're going to be doing something similar to that today. I see a few people got that one. That's good. Okay, so the lab we're doing today is going to allow us to figure out, like we said here, what is the effect of force and distance on work. Okay, so what we're going to do is we're going to use these little spring scales, okay, and some rubber bands in order to see how much work we do on a rubber band. Now, when we stretch a rubber band, how do we know that we're doing work? it changes shape. Okay, not only does it change shape, but now once I've stretched it, what does it want to do? Okay, it wants to go back to its original shape. Why does it want to go back to its original shape? What does it have now that it's stretched? It has potential energy. It now has the ability to do work because I did work on it. I stretched it. Okay, I exerted a force on it through a distance. Okay, in doing so, it now has potential energy. If I let it go, okay, it snaps back to its original shape. Everybody follow there? You've all seen how a rubber band works. Okay, all right. So in our lab, what we're going to do is we are going to pull back the rubber band to specified distances. That is, we are picking the distances to which we will stretch the rubber band. I tried to enunciate that. I didn't see anyone write that down, though. I don't see a lot of keyboards typing. Oh, because it's not loading. Okay. It wasn't because you weren't listening. Okay. Yeah, okay. Okay. So what we're going to do then, okay, we're going to pick the distances, and I think they're actually filled in on the chart already for you in your... They're not? No, they're not. But it says here what they're going to be. I think these are actually too big, the 10, the 15, and the 20. I think the last time we did this, because we got different rubber bands, they would not stretch that far. Okay, I mean, they could, but there's a certain range in which a rubber band stretches where it works properly, and then there's a range where you're actually permanently deforming it, and it won't work well after that. So I think what we'll do is we'll fill these distances in here, okay, as lower distances. Let's say, so we'll put in here that our first distance will be, let's say 2 centimeters. Sorry, it's supposed to be in meters, so we'll be 0.02 meters. Okay, and then we'll have, let's say, 0.04 meters. Try maybe 0.08. Okay, we'll skip a little bit. They won't be perfectly even, but that'll be all right. Let's go with 0.10. You know what? No, we can make them even. Let's go with 0.06 in there. 0.08, okay, 0.10, and 0.12, right? So we'll all have the same distances, and that's a range that this elastic band should be able to stretch to fairly easily, okay? And it'll remain in its truly elastic range for that, okay? All right, so we've determined the distances, okay? What we're going to measure is the force required to pull the rubber band back to those distances. Is that going to change as we go through? Yeah, I mean, if the further back you pull this thing, the harder you're going to have to pull it, right? Okay, so that's what we're going to be measuring, and that's what's going to change as a result of what we did. Okay, we are changing that. It's changed. The force should change, hopefully, as a result of what we do. Now, another thing that that's also going to change, you're going to have more than one responding variable in this lab. Okay, if I pull this thing back further, and I not only use more force, but what else is going to get bigger every time I pull it back? Okay, we already said force was going to get bigger. What else is going to get bigger? I'm using more force and more distance each time. What else gets bigger? The work, yeah, right? I should be doing more work on every single trial as well. Okay, I'm using more force over more distance, okay, so I should have that as well. All right, controlled variables. Anything that needs to remain the same throughout this experiment in order to make sure that stuff about the rubber band does not change. Okay, now, one of the things that I'm going to kind of explain to you here is important in terms of that particular, or one of those controlled variables. When we do this, okay, we need 2 desks for this. And we need to put the legs of 2 desks fairly close together so that, okay, the rubber band is just taut. Okay, if it's like this, it's no good. If it's already like this, it's no good. Okay, it needs to be just to the point where there's no slack in it. Okay, that's when your table legs are the right distance apart. And the best place to put them is actually just above the claws, or the little feet there. Okay, so there's the shaft of the leg, and then there's the foot at the bottom, and ours kind of go in right here. Okay, right? There's a little indentation right here on ours. That's where the rubber band should sit. It's kind of in the indentation of the two desks. Now, once you have that set, a person in your group needs to be sitting in each of those desks, and they need to sit there until the lab is over and not move. Okay? Why do they need to do that? Right. If the desks move, it'll change the condition of the rubber band. Okay? I need the rubber band to have the same initial tightness all the way through. If at some point the desks move and it becomes tighter, I'll use more force to stretch it than I did on the other ones. Okay? And then I won't have a controlled experiment. Does everyone follow? Okay? So the desks can't move during this experiment. Okay? So two people's job is going to be to sit in the desks and make sure they don't move so that that controlled variable stays constant. All right. You can see in this picture here that the setup's going to go as follows. We're going to have a ruler on the floor, okay, and we're going to attach the spring scale to both sides of the rubber band, not just one, okay, both sides of the rubber band. We're going to pull it back like this, okay, and we're going to record on our spring scale the force that's being used. Here's the problem. We ordered spring scales that were supposed to have grams and newtons on them. We got really excited when the boxes came because the boxes show a picture of a scale with grams and newtons on them. Inside the box is a scale with grams and ounces on it. So we tried to return them, and they said, no, we sent you the right boxes. And we said, we're not arguing about that. The boxes are fine. It's what's in them that's bad. And they refused to give us our money back. So we've never ordered anything from them again. Seems kind of petty, but anyway, okay. They have grams and ounces on them. Not a big deal. All you're going to do is take the reading in grams and divide it by 100, okay? And you'll have the reading in newtons. It's an approximate thing, but it's close enough for our purposes, okay? Now, the other thing you need to be mindful of is that you can adjust where the scale is, this little card that's kind of in here, okay? And you need to make sure that it isn't where it is right now, that when there's nothing on the scale, the tab is at 0, okay? So this little tab here, okay, needs to be on the 0 when you begin. If it's off, then your data is going to be off the whole lab. Okay? Everybody with me there? All right, so you put that on, you lay it on the floor, okay, and you pull it back along the floor to the specified distances, okay? And you need to be looking at it from above so that you're straight on with it so you make accurate measurements. All right? Questions there? So the procedure is pretty easy. You're going to pull the rubber band to a few distances and record a couple numbers. Okay? Procedure is pretty easy. All right. Okay, for our analysis and interpretation, there's a lot of wordy explanation here that may be oversimplifying. Okay, for question number 1, okay, it says we want to calculate the area beneath a force distance graph, okay, using half the base times the height, okay, in other words, half the maximum force exerted times the distance moved, which is what we were talking about here, okay? So we're going to multiply force by distance, okay, when we're calculating the area underneath the line of our graph. All right, so that's a fairly easy calculation, but I am going to want to see all of your calculations for each distance. Okay, sorry, you're only sorry, one calculation just for the total. Okay, is all I'm going to need to see there. The issue here is that you're going to have a graph that's going to be plotted by Google Sheets, and I want you to use data from the graph, not data from your chart. Okay, this is the same thing that's happening in your Need for Speed lab. These points are probably not going to be exactly on your best fit line once it's drawn. Okay, so you may need to calculate what x is at your largest y value. Sorry, what x is at your largest y value. Force is the y-axis. Okay, everyone follow me there? Right, so you'll have to probably calculate that in order to calculate your area. Okay. So let me re-explain that. We know that our largest distance is going to be 0.12 meters. Okay, we've decided that that's what it's going to be. What we need to know is what is our force at that distance. The point that we have there might not be on the line; it might be here. So the line is above that point. I want to calculate this triangle. right? So I need to know what is y when x is 0.12. That way I can calculate the area of this triangle. Something to watch for, though, is maybe that's not exactly a triangle, right? If you have a y-intercept that isn't 0, okay, then what you really have is this. A triangle and a rectangle, okay? And you'll need to calculate the area of both of those, okay? The y-intercept, which is b when it spits it out, okay, is the height of the rectangle, right? The height of the triangle is whatever your y value is minus b, okay? Then you can calculate both their areas. Does everyone follow there? Okay, so that's what you'll be doing for question number 1 in the analysis for this lab. Okay, and then question number 2, I want a fairly good explanation for this. Okay, I know it seems like a fairly simple question. What's the area underneath the force distance graph represent? What you need to do is look at what two things did you put together in order to get that. Okay, you multiplied two things together. When you multiply those two things together, what do you get? Maybe give me an explanation. Maybe mention things like, you know, what units you might arrive at, okay? Maybe mention the formula, okay, that looks similar to what you're doing there, but I want a bit of an explanation. That's the one that's as much as I'm going to say about that one, because that's the one that you guys need to kind of intuitively figure out for yourself, okay? All right, then after that, conclusion and evaluation, same as always. Sorry, I didn't talk about the hypothesis. I skipped right over that. Let's go back to hypothesis. Okay, so generate a hypothesis that explains how, using the materials below, we can calculate the work done on an object. If part of your hypothesis should talk about what work is. Okay, and we had a definition of that yesterday. The and part describes the experiment. The then part should tell me how you're going to calculate work using this lab. So here's something to think about. A lot of people will tell me how to calculate work twice in that hypothesis. Okay? I don't want to hear how I calculate work in the if part. I want to know what work is, not what work equals. Everybody follow me there? So if work is this and the experiment, then work can be calculated by doing this. All right? Okay. I think that covers it all. Safety. We are not shooting anything with the rubber bands. Is that 100% clear? Okay? It's all fun and games till someone loses an eye. Okay? Then it becomes a sport apparently, but okay, we're not going to do that today. Okay, we're going to just do this lab safely, easily. Okay, if your rubber band is still intact at the end of the lab, put it back in the bag here, okay, with the other rubber bands. When you grab a spring scale, there are two different kinds. They are labeled on the boxes as 500 and 2000. You need the 2000s, okay, so that they'll pull far enough. If you take a 500, you won't get good readings on it because you'll max it out right away. Okay, the 500s are green and the 2000s are red, just in case they ended up in the wrong boxes. Okay. You want the red ones. Okay? The scales inside are red. The boxes are all white. Okay? So you need a 2000 and one rubber band and at least a group of 3, at least. Okay? Because you need 2 sitters and 1 person to pull. Okay? Rulers are on the table. Everything else you need is there.